I will first, this talk before lunch break is going to be a case study, and I'm going to talk about some virtual testing we did, and also pseudo dynamic hybrid simulation we did. So I apologize if some of you were in the MTS office yesterday, because this is kind of a repeated information for you. We had a user group meeting for aerospace customers. So those are the data we just got very recently. I think it's a good case study to show to the people who actually could not make yesterday's event. So basically, I'm going to first talk about this example. This is a case study. So I introduce this example, and then again, there are two main parts. First part is going to be virtual testing of that testing example. And then I talk about hybrid simulation using the same test rig. So this is the example. We have been working on that rig for a couple months. There are different purposes. We want to use that rig to develop some new testing techniques. So this is sitting in the MTS building. It's actually an aerospace test lab. They are developing, new algorithms, new methodologies, and then using this test rig to validate some of those. So it's like a steel plate you can see here on top. This is your testing article. It's like a cantilever steel plate. And then there are 4 vertical actuators supporting this plate. So the idea here is to kind of simulate an aircraft wing, right? So then you can do a lot of proof of concept algorithm validation things on this. So that's the test rig we use. And the first topic I'm going to talk is about virtual testing, which essentially is like we want to model testing. So it's like everything is modeled on a computer. Then we want to learn from this type of virtual testing technique about, for example, system performance, some limitation of your actuators, or a lot of things. So why do we want to do this virtual testing? Because a lot of times these advanced structure testing are becoming more and more complex. Like actuator itself is highly nonlinear device, and the test specimen, especially when you are doing dynamic testing, they, having a lot of dynamic modes, and those are underdamped modes, meaning that their response is pretty significant, and they can be interacting with your dynamic actuators. And then, of course, the more significant one is the cross-coupling between different actuators. If you have multiple actuators pushing on the same specimen, then if one is moving, the other ones try to hold, but it actually will be, also dragged by this actuator. So all the others will, exhibit some kind of motion or force on top of them. But that cross-coupling causes a lot of control problems in advanced testing applications. So that's why we want to model our things, if we can, ahead of time to understand this complicated testing phenomenon, right? So this model can help 2 important questions. One is the capacity. So basically, can we do this testing at all? Do we have enough power, for example, hydraulic power, if actuator size is too small, to do this type of testing? So virtual testing can help you to answer that question, at least to some level of accuracy. And then another one is the fidelity. It's basically I want to kind of simulate my testing before I do the real testing, so I have some confidence about my testing performance. Then I have some basic idea about the testing results. So, and then another one is that using this type of modeling or virtual testing techniques, it's very useful for especially some people who are new to the testing work. Then you can sit in front of your computer, you can play with the model, do a lot of parameter sensitivity study, understand, for example, what is the PID gain is going to do to your testing system, right? Then without damaging anything, you can actually do a lot of load study as well. that's the motivation about why do virtual testing. Then in terms of the virtual testing, so there are three major parts we want to model. First is the controller model, right? So MTS has the proprietary models for our controller, which pretty much include everything you can see in a physical controller. And then the actuator model, of course, including servo valve and other things as well. Those are also MTS development. Actually, Brad Song, who's sitting over there, he's our control expert. He's the author of a lot of those models. And then the third major component is the test article model, the specimen model. So especially, as I said, if you have a multiple actuators sitting on top of a flexible specimen, you need a fairly accurate testing specimen model to understand the cross-coupling and to understand how the whole system behaves. Just under the hood a little bit, this is our controller model. Of course, sorry, maybe I just go one slide back. So this is basically a very surface view, right? This is the controller model, and then this is the testing, this is the actuator and the specimen. This is so-called plant in the control engineering terminology. Then, of course, that's the closed loop, where you can have, close the loop and do the control system. So under each block, there are like hundreds of blocks, sub-blocks inside there. But one of the main thing is this controller model. And we program everything here in MATLAB and Simulink environment because I think for control engineers, that's the most commonly used software framework. So you see, we can model our, in our controller, we have a stabilization gain, which we have the stability filter, forward loop filter, of course, the basic PID and other type of gains in there. It's all, it's all packaged in blocks like that in Simulink. Then the PID servo controller is actually a big S function written in C, then packaged into a Simulink block. So that's the controller model. The actuator model, again, is the S function and packaged in Simulink. And it actually models a lot of things, as you can see here. For example, the actuator, the piston unequal area, like, the leakage, a lot of things you can model in there. It's very high fidelity model, actually. And the servo valve, like the bandwidth, the filtering inside, the gains, low saturation, all those. And the hydraulic system also, like the accumulator and also your supply pressure, all those things. Those can be modeled. And another important thing is that it's completely scalable, this model. You can, build your virtual model with hundreds or thousands of actual control channels. There's no problem. There is no limitation at all for your virtual model, of course. But in reality, you need to be realistic as well. The point is that in the model, you can model any number of degree freedom, any number of actuators, and, even if you have some accelerometers, you can model inside there as well to do virtual testing. So, controller, actuator, and then the test specimen. So, in order to accurately simulate a real testing, the test specimen, you also need to model it. And we have a couple of different techniques to do that. Dr. Shawn Gao mentioned about it earlier in his presentation. But for this example, this case study, we actually, for that steel plate, remember in the beginning, that's the steel plate we are testing. And then we just built a FEA model first. Then we did a reduced order model out of that FEA model. Then that's the lower part, those two. So we convert the FEA model into basically this is a transfer function matrix model. So now we only care about the global dynamics, like what's the first mode, second mode, and what's the phase of that. Then why we do that reduced order modeling? Because it runs really fast. It preserves all the global dynamics, and then that's the main thing we care about in this testing. In this example, is that I want to see all the global dynamics. So we do a reduced order model to that. Then I'm showing you here is the virtual testing results. For example, these are 4 different actuators, and we have a step function. You know, if you deal with actuator tuning, sometimes, normally a lot of time we use a step function to tune your system. So we give a step function input. By the way, those are all in force control. And then this is showing the command force is the blue one, is the perfect step function. Of course, if you have some experience with a control system, then you see this is the response. The red one is the feedback, the simulated force feedback. Then you see there is of course, there is an overshoot. If your system, if your peaking is high enough, and then some oscillation, then finally you go to the desired force level. Of course, in our virtual model, we also can output all the displacement on all the actuators and the servo valve command, which used to drive all those actuators. Those are just some important signals that I'm outputting here, but essentially, using our model, virtual testing technique, you can output any signal inside your controller, then you can actually model those signals and output them as well. So you can do a side-by-side comparison and study like that. This is like a sensitivity study. So basically here is like I'm trying to see, you know, what if I have a different peaking, right? That's a lot of times when you tune a system, you first work on the peaking. If the peaking is low, like this green curve, of course, you need the dynamics is slower, so you need a longer time to reach the steady state. And the overshoot, of course, is also smaller because it's less aggressive peaking. But once you increase the peaking, becomes the red one, then you reach your steady state faster, but then you have more overshoot. That's just a more aggressive peaking. You know, that's just the thing I want to show you. For example, also, once you have a more aggressive peaking, especially on those actuator 1 and 2, you can see that this feedback started to becoming marginally unstable. You can see those very high frequency kind of a chirping signal in there, and it doesn't damp out over a long time. That means, okay, by this time, peaking of 8 is probably already too aggressive. In your real testing, you might want to back off from there and use a less aggressive one to start to play with your physical system, right? So that's another major thing is that I use the model, I can try to work backwards and then just to avoid any physical instability, because that's not, that's not fun. If anybody observe those physical instability, you just see this whole thing is like really going really fast and making a lot of noise, and hopefully not destroying any of your specimens. So another another parameter I want to show here is the leakage term. You know, the leakage across the piston, and so that's one thing I found, at least throughout this case study. It's very interesting because in the beginning I didn't think about this term at all. I thought, leakage, yeah, maybe for global dynamics, why do I care about that small parameter? But eventually we discovered it's actually very sensitive how you select this leakage term. For example, that's 2 different values we choose, and you see this in the unit of GPM per PSI. So when you have a different leakage number assumed in the model, and of course there is a borderline when you suddenly cross, then before that it's actually quite stable. Then after that it becomes very unstable. So that's another thing I want to show you. The model, again, the virtual testing model we have in MTS is a very high, it's a very highly complicated, and it actually models a lot of physical phenomena, and you can actually do that. So another thing is that we use that model, everything, we can do a real-time virtual testing too. You can do it offline on your own computer with MATLAB and Simulink, and you play with all those. But another thing is that we can actually go one step further. We can do a real-time version of that. We just build that model onto a real-time target machine. and then let the model run on the machine, right? And then, in the meanwhile, we can also give the same function generator and ask the physical test rig and run. So they are running in parallel. Basically, the same input running through the model, running through the physical rig, and then we can also get the response from either of them, both of them actually. Those two systems, they are interconnected through the shared memory technology. So basically, any signal appear on one of the machines will show up on the other machine. So what we do here is that we just did, online validation. First, we thought, okay, the model runs in real time. The model runs very, very fast. This is running at the 1024 Hertz. That's the sample rate we use. So it actually runs really fast. And also, we just do a real-time online validation. So that's what shows up on the real-time target machine. Basically, the blue curve and the orange term, one is from the real test rig, the real feedback measurement, and one is from the the response. And you can see they are pretty accurate. So I'm just here showing some, and of course, on the controller side, you can collect all those signals as well. So this is showing from the controller side at peaking equal to 4. This is actuator 1 performance. So actually, it's not too bad. We capture basically the dynamics here, and then you can see here also at the end of this step function, there is also some kind of a transient response, and the model also captured that pretty well. Actuator 2 actually is much better. It's just like the physical test. Each actuator, they behave a little differently. The rig setup is not perfect. So in our model, we assume all the actuators, they are identical. We use a nominal parameter to do all those kind of simulations. So actuator 1, we see somewhat a little bit less accuracy, but actuator 2 is more accurate. And 3, same thing, it's quite good. We are happy about the model to capture the physical behavior. So that's when you go up to peaking equal to 8. Again, this is more aggressive peaking, and you see the overshoot now is more because it reaches to about 800 Newton. Before it was 500 or 600. So more aggressive peaking, still we can capture those behavior. And you can see here that's where the marginally it becomes unstable. And if you see very closely about the model performance, it actually also shows some of that behavior. So in general, that's about the first part of my presentation. It's virtual testing. Basically, we can model a lot of the testing by just playing with the computer model. Then the hybrid simulation. So hybrid simulation, we already had a lot of talk. I think you know about that. So basically, the philosophy for this hybrid simulation is that I break down, right? The part of that is the computational substructure, part of it is the physical substructure, and how do I choose which part to test? So the philosophy is you model that part which you have more confidence. If, for example, like structure building, you might have a pretty good model about the structures, but like in a lot of the examples we talked previously, especially in Dr. Dyke's talk. So, for example, the MR damper thing is highly nonlinear and it's very complicated behavior. When you give a different current level, it behaves differently. So those are the things you may not be having a very reliable model, then you test that part. So that's the fundamental philosophy about the hybrid simulation, right? So I'm not going to go too much into this. Dr. Shawn Gao already introduced about that. And that's the CSI approach. We have 2 different approaches. We can involve a real-time target machine to do hybrid simulation. And if you have some budget limitation, if you want to just do a slow hybrid simulation, you just need to get the CSI software from MTS, then connect to your FDX and with the physical rig. Then you don't need to buy additional hardware. So CSI is just a software. So in this example, that's the case study example I was trying to show you. So for example, this is a physical substructure. That's the steel plate sitting there in our test rig in the lab. And then we just assume a longer part, extend that by a longer part because the airspace wing, airplane wing is actually longer. Into at least the ratio is actually, we just want to demonstrate that concept. So essentially, we extend that plate by including a computational substructure. These are modeled in OpenSeas, and then this is the experimental element implemented in OpenSeas to represent this physical substructure. And then that's how we perform this case study example. In here, inside the computational substructure, inside OpenSeas, we apply some type of load into this numerical computational substructure. Then OpenSeas is going to solve to get the response at the interface node, right? This is the interface node where we actually join the physical substructure and the computational substructure. So FEA is going to solve, and once it solves, it will get the we are here doing a 3-degree freedom. So the UZ, which is the vertical, and the bending about the 2 different horizontal axes, right? Rotational X and rotational Y. Because we have only 4 actuators, we can only apply those 3-degree freedom. So FEA is going to solve those at the UZ, rotational X and Y. But then, of course, in order for the physical actuator to apply those, so those are in the global space, global degree freedom. But the actuator needs to know what's my load code in my actuator space, what's the command. Then we need to do some POF transformations in order to drive the actuators so that those 4 actuators is going to drive that physical plate to represent those 3-degree freedom. And then, after that, then we will get the feedback from those actuators and convert them back into the global degree freedom, the FZ, right, force in the Z direction, and the moment in the X and the Y direction, because that's what model cares. In the OpenSeas model, it only cares about this in the global degree freedom. So we feedback those force into the numerical substructure, then we solve for the next step. That's generally how we deal with this hybrid simulation. So the computational substructure acting as a driver, it solves, and then it drives the physical system. The physical system have a feedback, goes back to the model, then solve and solve, just like for each time step. So here, I don't want to go into too much detail. Shawn, you mentioned about this, and I think Brad Stone also will talk about this more in detail. So basically, that's the degree of freedom transformation we need to do from the model space to the actuator space. So we can implement it in the calculation channel inside the MTS controller. So we use the MTS Error Pro software in this case study, but actually in the 793 software, which I think most of those civil structure labs use the same thing. We have that capability to do those calculation channels. So this calculation channel actually allows you to do a lot of things, not only the simple, mathematical operation like the plus minus or, combine signal or whatever. It actually has even like functionality to do digital signal processing, to do different advanced filtering techniques using our that's all built in our controller. So just, a quick introduction about that. This demo video, somehow it didn't work. I tried to work it out, but it didn't like it. I'm going to show you here actually in the, didn't work here either. So, I open a different video file, have it play, edit. Thanks, Paul. So, yeah, that's basically basically the testing, we did. That's basically, you see, that's the physical plate being tested over there, and you see, it's very flary. Here, that's the extended part. You can see that's the extended part modeled by OpenSys. So when we solve, then we drive this physical rig, and then we actually start the whole loop. That's the whole cycle of the hybrid simulation, and you see some responses there. So again, this is just a proof of concept. It's a different type of application. Not many people in the civil structure field doing those kind of shell element or plate type of testing. But we just want to show you, in OpenSys, it does have the capability to do not only beam column elements, but also shell elements, solid elements, any elements it developed. You can use those to do hybrid simulation. So of course, for this test rig particularly, it's not ideal for demonstrate this because you see those 4 actuators, they are connected by a flexible specimen there. Then when you try to apply those degree freedom motions, they all interact with each other. It doesn't track very well. But like this system is more perfect example to demonstrate. You have a rigid loading beam, so you can very accurately control the motion and the force at that loading point. So that's the thing we are going to focus by the UMN folks. They are going to introduce you about that. So lastly, that's pretty much, I will just show you quickly some results, of course, the data. So we have the command. Those are the 3. The test you just saw, where you have 3 degree freedom, right? The Rx, Ry, and the UZ. The command, feedback, and also the force. Those are all from the testing. And then the individual actuator force, of course, you can take a look at that. And a lot of people also do distributed hybrid simulation. So you see, let's see, this is one system getting here, like in EcoPoly in Montreal or in Springburg in Australia. They all have a similar mass system. They can actually all link together to do a distributed hybrid simulation as well. So in conclusion is that, it's a trend we combine more and more modeling technique with testing techniques to do either virtual testing or hybrid testing, those type of things. And the virtual testing gives you a lot of, knowledge of before you have a physical specimen even constructed. You can use this type of virtual testing technique to understand your system and predict some response. Then hybrid simulation, of course, the main motivation for that is cost effectiveness. So you can actually do it fairly, cost effectively. And it's proven technology. See, we have a lot of applications. That's the end of my presentation, and we are ready for lunch.